So I'm going to be talking about. So honestly, I kind of wavered a little bit on what to talk about in this talk because usually, if y'all have seen me talk before, I usually talk pretty monomaniacally about binary black holes. It was kind of my bread and butter for a little while. I have thrown those completely out of this talk. This is going to be the first talk I've given, I think, that except for one aside and one slide does not mention LIGO at all. So gravy wave people, y'all can leave. Please don't, but you can. Instead, I'm going to focus on a couple different things. Since this is the CCA, I'm going to talk a little bit more about the computational methods behind what we do than I normally would. Normally, I have like one slide on our in-body code, and I'm like, yeah, you can download it, run it, have fun. Here, I'm actually going to get a little bit more into the method and the philosophy of it. Not too much. It's not a 60-minute methods talk. Don't worry. But what I'm going to do is I'm going to talk about that a little bit more to give you a sense of why we use the code we do, what we can model with it. And then I'm going to talk about two cool things we've been doing with some upgrades to the code recently. So one is going to be, how do you model massive black holes? So intermediate massive black holes, supermassive black holes in the middle of a star cluster. Think Sag A star in the middle of our galactic center, or the IMBH in Omega Centauri in the middle of Omega Centauri. And the second I'm going to talk about is, how do you model what happens to those star clusters as they're pulled apart by their host galaxies? So I don't think I need to sell people here on why stellar streams are cool. I have one of the preeminent cheerleaders right in the front row here. But I want to talk a little bit more about how we model this and what you can and can't say about stellar streams from our understanding of stellar dynamics. So when I talk about star clusters, this is what I'm talking about. There's kind of a lot of different things that fall under this general heading. Typically speaking, though, what I mean are old, dense globular clusters. So things like 47 Tuc, M22, things we find in the Milky Way and in other galaxies. So on the left here, I'm just showing a nice classic, I think I stole it from Wikipedia, picture of 47 Tuc. You've got the nice central structure, the luminosity increasing towards the center. On the right, I have a synthetic observation of a young massive cluster that we tried our damnedest to create as a pseudo-observation through JWST. We took all of the stars from our in-body simulation. We passed them through the correct JWST bandpass filters. We learned a lot more about how you actually make these false color images, which, being a theorist, was pretty novel to me. The nice thing about this, though, is that once we have these simulations, right? Once we have an in-body simulation, we can turn the crank forward. So we're not limited to just a single state of this cluster. We can actually take this at 0 main sequence, and we can turn the crank forward, right? And we can see what this thing looks like many millions or billions of years in the future, both through the early phases, where you have a lot of fun binary dynamics in the center, and in the later phases, when you're starting to lose a lot of mass to the galactic tidal field and really form stellar streams. This movie, by the way, was created by Inés Rodriguez-Shu, who was a dual physics and art major working with my group. So it was a really fun opportunity to find a project where we really combined those two sort of genres. And so instead of my normal spiel where I talk about gravy waves, what I'm going to do is pose a different question, which is, what can star clusters do for you, right? In this central region, I have a very high density of stars. I have many close encounters between stars and binaries. I have collisional gravitational dynamics that's driving the evolution of the star cluster. And so it turns out that in these dense regions, there's a lot of things you can find and a lot of things you can produce that you do not find anywhere else in the universe, right? You can't produce a lot of these things through isolated binary evolution. You can't produce them through chance encounters in the galaxy. And I'm talking about things like, well, these you can produce, but the rates are substantially higher because of this dynamics. So when we look in the cores of globular clusters, we see an massive overabundance of X-ray binaries, a massive overabundance of cataclysmic variables. Binary black hole mergers, we think, are produced about 100 times more efficiently in star clusters than they are in the galactic field. You see rejuvenated millisecond pulsars that are extremely old. You see stellar collisions, which you don't see in essentially at all in the fields of galaxies. And in the central regions, you can really start to grow massive objects like the kind that we're interested in for both TDE and other physics, right? I can start to grow intermediate and supermassive black holes, right? And I can even use these star clusters as ways to trace galaxy assembly, right? I can use them as probes of when were certain galaxies absorbed by other galaxies, what happened to those globular clusters, and I can even ask, what do these stellar streams give us in terms of probes of dark matter? And so what I'm going to focus on today, after I give my little numerical introduction to how we do this, after I give my little numerical introduction to how we do this, is the first one of these, which is how do we grow intermediate and supermassive black holes, right? I assume everyone here has heard about IMBHs and SMBHs in one context or another. Yay? Yay. So I'm still, however, contractually obligated to show this plot showing the mysterious question mark between supermassive and stellar mass black holes. I honestly find this a little bit irritating because it suggests a sort of evolutionary path, which I don't necessarily believe. But there is a question: why are there not things in the central region here? And is there a way we can actually grow from stellar mass to intermediate mass to even supermassive black holes? Now, in this case, there's been a lot of claims of intermediate mass black holes observed both in the Milky Way and in the local universe. These have been going back well before my time. And there's even been a lot of claims of intermediate mass black holes. These are things between 100 and roughly about 10 to the 5, 10 to the 6 solar masses in Milky Way globular clusters. Most of those claims have gone away relatively quickly. There is one exception to this, which I absolutely adore, which is that about 2 years ago, over the summer, this paper came out in Nature. And so the problem with the previous detections of intermediate mass black holes in Milky Way globular clusters is that for the most part, they relied on either somewhat convoluted statistics that doesn't necessarily hold up to more data, or methods that were very dependent on your particular dynamical model. It was very, very difficult, because the black holes are typically smaller and right in the center, to really find some analogy of the S stars like we have around Sag A star, right? With the S stars, it's really easy to measure the mass of Sag A star because you literally just trace these orbits out. That's really hard in the central regions of a globular cluster, unless for some inexplicable reason you had focused HST on the center of that cluster over 15 years, like basically once a month, and put that all into a catalog. Nobody gets that amount of HST time, obviously. Hubble time is very expensive. But what the authors here realized is that the core of Omega Cyn is an HST calibration source. For one of the cameras there, every time they needed to calibrate the I think it's the WFC3 camera, they just pointed it at the core of Omega Cyn. And so if you go through and you clean that up properly, you can actually build a proper motion catalog of the core and central region of Omega Cyn, down basically to, I want to say it was about 25th magnitude, something absurd that you would never ever get just from ground-based observations. And so in doing so, they find 7 stars that seem to be moving faster than the local escape speed. And so you don't get a full-on population of S stars because there's no real cusp around this supermassive black hole, but there is some little object here, right in the middle of Omega Cyn, that 7 stars seem to be moving substantially faster around than they would be otherwise. And so to my mind, this is the first believable detection of an intermediate mass black hole in a globular cluster. It's difficult to place exact constraints on the mass. You can't get full orbital solutions, but you can place pretty reasonable constraints on the minimum mass of at least 8,000 solar masses. And probably, if you believe our in-body models, which you sort of should, it's probably closer to the 30, 40, 50,000 solar mass range. So a genuine bona fide IMBH, about 5 kiloparsecs from Earth. So that's cool. What does this tell us, though, about a lot of the things that we're interested in from black holes, right? What does this say about the rate of mergers between the massive black hole and stellar mass black holes, potential sources for LISA? What does it say about the TDE rate? You know, how do we actually answer questions like that? The other question that I'm going to pose, and that I'm going to get to a little bit later, is stellar streams, right? I don't need to sell people here on why stellar streams are interesting. I just have one quick slide to do that. Essentially, as you strip the stars from star clusters in a galactic potential, they end up wrapping around the Milky Way, or whatever host galaxy they're in. These thin stellar streams, as you pull the star cluster apart, then offer essentially a perfect, purely photometric tracer of the galactic potential, right? Normally with an orbit, you have to actually model the thing forward. You have to integrate it forward to see what the orbit looks like. With a stream, you literally just go look at it, and it traces out the entire orbit. And so it gives you a way, using just purely photometric detections, to map out the orbits, and therefore map out the dark matter potential around a galaxy. So not only can you measure the dark matter halo itself, you can also measure substructures in there. If, for instance, I have a gap in the stream, like is observed in the GD1 stream, I can maybe say, okay, this might have come from an interaction with a dark matter subhalo. And that helps me place constraints on the nature of dark matter. or at least how low in mass the dark matter subhalo function goes. And so people are really excited about, both at the CCA and a bunch of other places, using these streams as potential probes of the dark matter halo of the universe, or of the galaxy, excuse me, of the universe. Until I've had too much coffee at this point. All right. And so as a modeler, there are two things I need to really make this work, right? First, I need a good model, duh. In my case, that's an in-body model, or how we model these star clusters forward in time. The second thing that I need are some decent, believable initial conditions. Right? These are sort of the two key ingredients at a very, very Mickey Mouse level for any good simulation-based project. So I'm going to talk about both of these in their context over the course of this talk, but I'm going to start off talking about the in-body code that we use, because it is actually pretty distinct in the realm of in-body codes. I don't think anyone here has used things like it, at least not to my knowledge. And so I really want to give you a sense of how these Monte Carlo-based methods actually work, because I think this is something that people will find particularly interesting here. All right. So how do I solve the gravitational in-body problem? Well, there's the really easy and really stupid way. That's what basically everybody starts with. And it's also why this field is a little bit tricky, because people look at it and they say to themselves, okay, how hard can this actually be? And then they spend 30 years messing around with triples and other close encounters, and there's their entire career. And the reason it's naive is because, well, it's a freshman physics problem, right? I have some in collection of particles. I can calculate the pairwise force between each of those particles, easy peasy. I add that together and I get myself a total force. I basically learn how to solve ODEs the first week in a computational physics course, and then this is easy. I have F equals ma, I solve that forward. How hard can this actually be? Now, I think we all know that there are some additional complications to this, but in the star cluster case, there's two very, very important things that we actually want to do. One, we want to be able to resolve the effects of binary stars. And there's two reasons for that. One is that, the binaries produce a lot of those interesting astrophysical things I was talking about earlier, millisecond pulsars, binary black holes, things like that. But the second is that in a globular cluster, a single binary star, single hard binary, can have as much binding energy as the entire cluster itself. And as we actually know at this point, the hardening rate of those binaries, the interactions between that binary and the other stars, is what holds the cluster up against continued collapse. So you can't ignore the binaries or marginalize over them. They're actually integral to the long-term evolution in a way that, for instance, in a cosmological simulation, you actually very much want to avoid forming binaries between your particles, which is a long-winded way of saying, compared to a cosmological simulation, I can't use any softening. Any amount of softening here would completely kill the interesting binary dynamics that both are what I'm interested in from a transience and a binary perspective, and key to the overall global evolution, right? And so what that means is that I have to allow binaries to form, which in turn takes my potential 1 over r to infinity and grinds my time step to a halt, right? I have a tight binary in the middle of a cluster. This can have an orbital period of maybe days or tens of days. Meanwhile, the stars in the outer regions of the cluster are going around on 10, 50 mega-year orbits. And so I have this massive range in timescales that I have to resolve in order to turn the crank forward in this. And like I said, in a globular cluster, and in a lot of these star clusters, the interactions between the binaries and the other stars are critical to following that long-term evolution. Now, what I mean by that is the following. This is an example of what's called Heggie's law. For those of y'all that really paid a lot of attention in Chapter 7 of Binney and Tremaine. What Heggie's law is actually saying, though, is the following. Is that, let's say that I have a binary in the center of my cluster, a binary star. I'm going to throw another particle at this, right? So it's basically just a scattering encounter. If you're particularly self-loathing, you could imagine this as a particle physics experiment. You could calculate cross-sections. In fact, if you look at some of the papers from the 90s, the appendices are all just energy-based cross-sections. They look like nuclear physics collision experiments. Very, very long. But fortunately, we don't have to do that anymore. You can just fire up a small in-body integrator. But I don't even need to do that, as long as I'm really, really good with the math and I can make a decent, detailed balance calculation. And so Douglas Heggie showed this about 50 years ago, where he noticed that on statistical average, if I have a binary that's what we call a hard binary, I've used that term a couple times now, and I'll define it now. But a hard binary is just something where the magnitude of the binding energy of that binary is greater than the typical kinetic energy of other particles in the cluster. In other words, the binding energy I have in my binary is greater than the kinetic energy I have of the two things coming at one another, right? If this was all equal mass, you could even rephrase that in terms of velocities. So this would be the orbital velocity here is faster than the center of mass velocity of the two towards each other. But the energy term works regardless of the mass ratios. And so what Douglas Heggie showed, using this very beautiful 50-page detailed balance argument, is that on average, these three-body encounters between stars and binaries will tend to harden hard binaries and soften soft binaries. So I'm going to throw a single star at this binary right now. You're going to see that it's going to undergo many interactions here. This is a formally chaotic problem, right? I changed the initial conditions slightly. The entire thing goes completely differently. But this detailed balance argument means that on statistical average, the behavior of this is predictable. So after many, many scrums here, many close, chaotic, what we call resonance patterns, right? What you're going to see is that I have a new binary that is produced in this and another particle that is shot out. And if you're really, really careful, and I can play this again, actually, what you'll notice is two things. One, well, three things, actually. The first one's not relevant to what I'm talking about. The first thing that's irrelevant is that I actually do exchange the two particles. That's cute from a chromatic perspective here, but not actually relevant. From a dynamics perspective, though, what's interesting is that, and you'll see this again when these things break apart, the binary that is produced has a shorter orbital period, which means it has a higher magnitude of a binding energy, and the two particles leave at a faster velocity than they came in with, right? I'm converting the binding energy of that binary into kinetic energy of the recoil. Essentially, this is powering the cluster against continued collapse once I hit core collapse. If I really wanted to, I could think of this as nuclear fusion in a star, right? Things are coming inwards, everything's collapsing inwards. Eventually, I reach a high enough density in the central region that I can facilitate these binary interactions that then produce energy to hold me up against continued collapse. It's even self-regulating in the same way that stars are. And so what happens to the binary is that it shrinks, gets a recoil kick, is thrown out into the halo of the cluster. Once it's out here, dynamical friction brings it back in, which heats up the cluster even more. And this process basically just continues again and again. And each one of these interactions is critical to holding up the cluster against continued collapse. I don't know why that's doing a slow fade, but such things are unknowable. But this is the problem, right? I need to resolve this very careful, very precise binary dynamics, and I need to resolve 1 million or maybe even 10 million particles over a Hubble time of integration time, right? It's a very difficult, disparate spread of time steps and time scales that makes this very, very hard. So whereas collisionless cosmological simulations routinely deal with particle numbers in the trillions or even higher, fully collisional in-body simulations are way behind the times there in terms of in-body numbers. So this is a nice plot going from basically the 60s up to 2000s, showing the number of particles that have been done in an in-body simulation as a function of publication year. You start off with tens or maybe a few tens in the 60s and 65, up to about 10 to the 5 in 2000. The state of the art as of about 10 years ago, which hasn't really been improved on all that much, is from 2016 by Long Wang, who did a simulation with 1 million particles of a globular cluster over a Hubble time of evolution. This took 13 months of wall time on a highly parallelized GPU cluster out of either the Max Planck or Heidelberg, I can't remember. So we like to have students graduate having run more than 1 or 2 computational models. I mean, that's not a requirement. I think people get away with not doing that. I prefer to have large sweeps of models where we can actually explore the parameter space much more leisurely and much more completely. And so the question is there a way we can compress all of this very complicated dynamics that I have to resolve into something that can be done a lot faster? By the way, these plots here, this is just a pseudo observation of what this million body star cluster actually would look like. The cluster is here. All of the things around here are just the different species of stars. So main sequence stars, red giants, black holes, yada, yada, yada. All right. And so what we do instead is the following. We say, okay, the primary driver of collisional evolution in a star cluster is 2-body encounters, right? This star interacts with this star. They exchange energy and angular momentum. It's essentially like collisions between particles in a gas. except here it's collisions, two-body collisions between stars in a cluster that allow you to exchange energy and angular momentum. And so what we can do, though, is I can say, okay, I know from just, bread and butter Kepler's laws how much my star is going to be deflected by some angle if it just encounters another star on a hyperbolic orbit, right? I can calculate based on its velocity and its impact parameter what this angle of deflection is going to be. I can integrate over a large number of stars in the cluster, just integrating out in terms of impact parameter, add that all together, and I can calculate a mean value of that deflection per some unit time, right? This is just basically keeping track of the integrals. It's pretty straightforward to do. What our Monte Carlo method does, this was originally developed by Michel Hennon in the early 70s, is we say, okay, well, I want to be able to do this kind of relaxation. I don't want to model the interaction between this star and every other star. I'm just going to grab the nearest star to me. I am going to undergo a single Keplerian hyperbolic encounter with this star, but I am going to tune it such that the angle of this effective encounter is equal to the angle I get by calculating the mean field integral. Right? So I calculate this averaged quantity. I set up a real two-body scattering, and I just tune the two-body scattering to have the same deflection angle as I would get from many two-body encounters. The advantages of this are twofold. One, it's a hell of a lot faster, as you can imagine. And two, it explicitly conserves energy and angular momentum, unlike essentially every other Monte Carlo method out there. Because when I change the energy and angular momentum of one star due to its deflection, I'm changing that of its companion star or its partner by the same equal and opposite amount. So I'm baking in energy and angular momentum conservation to the dynamics by doing this. So how does this work in practice? Well, Hennon's method basically says the following. I'm trying to model a spherical star cluster, right? I need a few ingredients for this to work. First of all, I need a gravitational potential. I am a fundamentally lazy modeler. I don't want to actually solve the n-squared potential. So I'm going to notice that to lowest order, globular clusters are basically spherical. So I'm just going to literally compute these as spherical shells. And this actually works mathematically on an orbit averaging sense. I can actually treat these as spherical shells to lowest order. And so I assume my cluster is spherically symmetric, which means I can then go back to my intro physics class and say, okay, well, if these are all just spherical mass shells, the potential is trivial between any two stars, right? It's literally just dominated by all of the mass that's interior, and everything exterior to that I ignore. So I can even do this if I'm so inclined in a single for loop calculation. So that's really nice. And so what I'm going to do is I'm going to say, okay, I have all of my stars here. I'm going to focus just on the interior two stars here, because I still need some way to actually pair these things up for those two-body encounters I was talking about. So I'm just going to take my first two stars here. I'm going to call this I equals 1. I'm going to call this I equals 2. And I'm going to perform those pairwise encounters just by counting up in terms of radius, right? So I've sphericalized my star cluster. I'm counting outwards from the first two stars, and each pair of stars are the two that I'm actually going to perform those two-body encounters with. Essentially, what I am doing is, in a somewhat grotesque fashion, turning my in-body star cluster into something that looks a lot more like Mesa, right? It's kind of weird, and it's even weirder that it works as well as it does. So I have these two particles. I'm going to perform those two-body encounters. A nice thing about this is because I am also calculating, in order to calculate that deflection angle, I need all the usual local quantities like number density, velocity dispersion, all the things you would imagine go into this problem. That also means I can very easily calculate the probability of having a strong encounter. So I can calculate the probability over some time step of two stars colliding, or a binary star interacting with a single star, like I showed earlier. That's really easy. That's just in sigma v. I can do that and flip a coin and decide to do an encounter or not. Turns out in sigma v also works a lot better than you would expect, even in regions where the mathematics say shouldn't. So I do these two-body encounters. What that's going to do is that's going to push my stars onto new orbits, right? Because I've exchanged energy between those two particles. And so if these were my original orbits of blue and red here, I'm going to give these things a kick due to their two-body encounter. That's going to put me onto new orbits, right? Now, in a spherical potential, these orbits are defined purely by their energy and their angular momentum and the potential, right? Just three numbers. Well, two numbers and a function. In order to calculate where these stars are going to be on their next time scale, I don't actually need to integrate them forward in time in a potential, because since the entire thing is spherical, it obeys a 1D energy equation, right? I just have energy plus the centrifugal term minus the potential, or plus the potential, and I'm done. So what I can do is say, okay, this tells me what my radial velocity is with respect to the cluster. I just pick a random new position based on that radial velocity. I assume it's more likely to draw it where it's moving slower. I sample from that, and I get new particle positions, and then I'm done. All I have to do, the only thing that I have to do, the only thing that makes this computationally a little bit tricky, is at the end, I have to resort everything in terms of increasing radius. I say this because the CS people know that sorting, unlike everything else I've described, is an n-log-n process, right? And so that is the computational bottleneck of this. It essentially beats the n-squared scaling of direct n-body. So I'm not having to add the forces together. The hardest thing is literally just I get new orbital positions, and I have to move everything around. And so the Monte Carlo sampling really comes from two different places in this. First, I'm picking a random position for my stars along each orbit. They're consistent with their real orbits in the cluster. And then I'm allowing for the possibility of close encounters, which is also done with a coin flip. All right. Any questions on that, by the way? It's a really weird way of thinking about in-body dynamics, right? Like, it really is in some ways more similar to MESA than it is to a traditional in-body code. All right, cool. Yeah.
So when you do the strong encounters, are you doing those, you're handling those differently, or are you still handling them the same way?
No, so those are not done with super encounters. The nice thing about the strong encounters is we can do those explicitly. So when we have an encounter between a binary and a single star, we actually fire up a small in-body integrator, which is super fast, and just resolve the outcome of that scattering experiment. So the one I showed earlier, the Curlicue movie, is actually from our small in-body submodule. We can do the same thing with tidal captures, physical collisions, basically any of the gooey microphysics that makes binaries and single stars and clusters really interesting, we can throw in pretty trivially.
And this has been tested that reproduces statistically the same result.
Yep, I've got that in like 2 slides. So this is our code. It's called the Cluster Monte Carlo code. It's been developed over 20, 25 years at this point, starting well before my time. And it essentially does what I described, right? It models the cumulative effect of many two-body encounters as pairwise effective encounters. This is done in, for those of y'all that really remember your Benny and Tremaine, the Fokker-Planck approximation. I sample the positions and velocities from my distributions, just based on the potential and the velocities, and I can add in as much of that fun microphysics like stellar evolution or binary encounters that I want. The nice thing about this is that it lets us crank up to 10 to the 6, 10 to the 7 particles, enough to model realistic globular clusters and galactic nuclei pretty easily. Both of these codes are public, by the way. So our cluster code CMC is not pip installable. It's a C-based code, but you can download it, run it, install it, send me emails about the ways that it's not running. I will fix them when I fix them and iterate thereon. We actually use as our stellar evolution module Cosmic, the population synthesis code, which is pip installable. And they're actually connected at the repository level. So anytime you make any updates to your stellar evolution code, they are essentially automatically get pulled into the repository for CMC, which is pretty nice. If I want to model an entire galaxy's worth of stars and binaries, and then compare that to the stellar evolution of the clusters, it's really easy to do that using an apples-to-apples approach to stellar evolution. All right. So does it work? All right, that's a pretty reasonable question. Short answer is yes. Right? If I evolve this thing forward, right, I get the sort of normal gravitothermal evolution that I expect. My inner regions of my cluster contract inwards. My outer regions expand outwards. As the thing approaches core collapse, I get a very nice, very mathematically predictable profile for the density of my cluster. This is well predicted from old Fokker-Planck models, but essentially the mass density at core collapse goes as radius to the minus 2.23 power. We recover that over, I think it's 15 orders of magnitude. So we reproduce well-known things from the literature from 20, 30 years ago. If I compare it to that in-body simulation I was showing earlier, we essentially get almost spot on agreement between the half mass radius of the evolution and the core radius of this. We get the outer regions a little bit wrong, but that actually has to do with differences in the tidal physics between the two codes. That was a little hard to sort of pin down. The nice thing about this is, whereas the in-body model took 13 months, this took us 2 days. So we can actually study star clusters. I appreciate the little clap on a realistic grad student lifetime. And we can study entire suites of star clusters. Okay, so that is my long-winded, I'm at the CCA, here's how in-body works tutorial. Now I'm going to switch to a couple of fun things that we've done with the code lately that I want to tell you all about. So the first thing I'm going to talk about is how do we create intermediate mass black holes, right? How do we create things like the IMDH and Omega Centauri? How do we maybe even create supermassive black holes? That part's still in tentative. And basically, if I want to create massive black holes in the center galaxies, there's 2 ways I can do it. Right? If I'm ignoring gas, which I'm doing for the time being, apologies, then there's really just 2 ways left I can do it. First, I can repeatedly merge stars, black holes together and grow up as a black hole, massive black hole that way. This would be sort of your first thought, but it turns out it doesn't actually work very well for the following reason. If I have 2 black holes that merge, right? They produce a black hole that's roughly twice the mass of the 2 that went into it. It gives it a new large spin. The problem is, with that large spin, I actually give a preferential direction for gravitational wave emission. And so if I find myself another partner and I merge again, what happens is I get a massive recoil kick due to the emission of gravitational waves. This doesn't happen in the first generation if the black holes aren't spinning. But the second I have a black hole that is spinning, I suddenly start to get very large recoil kicks. And these kicks can be extreme. So if I have black holes with large spins, these can be as high as 1,000 kilometers a second or more. Escape speed for most star clusters is 10 or a few tens of kilometers a second. So most of the time, I can't actually daisy chain these black hole mergers together. I get maybe a couple of generations in, and then they just get clean yeeted out of the center, and I am basically back to where I started. So that doesn't work. So let's look at option B, which is frankly a much more fun, which is I can create a massive black hole seed by merging massive stars together so quickly that I actually prolong the lifetime of these stars, and I form a hypermassive star of hundreds or even thousands of solar masses that can eventually collapse to a massive black hole. So the idea here is the following, right? Let's say I start off with 2 separate stars, 100, 120 solar masses. I merge these together, I get a 200 solar mass star. If I'm worried about, for instance, my massive stars being destroyed by parent stability supernova, this is just a sort of throw in for the gravitational wave people, the nice thing about this is I can actually sidestep the parent stability gap entirely, because I can cook up stars that have much lower core masses. But the other nice thing about this is each time I do this, 2 things happen. 1, I rejuvenate the star, so it's going to live longer, which gives it more opportunities to merge with other stars. And 2, I puff up the star just from the injection of energy into it in the merger itself, which makes it even easier to hit this thing again, right? If I imagine this as, again, just a target hanging out in the center of the cluster, right? The likelihood of a collision is given by the radius of the star squared to lowest order, right? It's literally just a geometric target. If I puff the star up during these mergers, I have an easier to hit target. Right? And so this is an idea that goes back 20, 30 years. These are called collisional runaways. But the idea is if I start a merger early on, it's actually easier and easier to keep merging and potentially have a runaway that produces these massive seeds that are possibly the progenitors of intermediate mass black holes. So what we need for this to work are very dense, very, very compact clusters. Fortunately, this tends to be pretty copacetic with what we see of star clusters in the local universe. So observations tend to prefer star clusters that are actually both flatter profiled and denser than what we see in globular clusters in the local universe. And like so many things in astronomy, we just write it down with a power law. So this was first noted, at least in this functional form, by Elson in the late 80s, which is that if I go look at young star clusters in the LMC and SMC, they actually just tend to follow a nice simple power law up here. Right? You also need this, it turns out, to explain the current densities and velocity dispersions of present-day globular clusters. So for instance, the cluster 47 Tuck, if I try to model this starting from a King profile or a Plummer profile, it turns out to be really hard to match both the density and the velocity dispersion profiles by the present day. If I start off with a flat Elson profile, though, and Claire Yee showed this very explicitly a few years ago, that's basically the best I can get in terms of matching the present day properties of these star clusters. This is also something that's backed up from simulations. So this is a movie I stole from Mike. He's not here, so I can show it. But basically, if I look at these cloud collapse simulations, right, what I see is that star clusters form hierarchically, right? I fragment my gas cloud, and I start forming pockets of stars here. But very quickly, basically within less than a couple of free fall times, these two clumps are going to recombine and form something that, again, looks very similar to that Elson profile. So this is found both in simulations and in observations. And so if we start off with these dense, sort of flatter profiles, can we produce these kind of collisional runaways? And so the answer is yes, otherwise I wouldn't be talking about this. And I'm going to show right now one of these collisional runaways from a paper done by Kuldeep Sharma, who's a PhD student in my group. He graduated last year. So it starts off with the merger of two binaries, right? This is one of these binary-binary interactions, where in this merger, I actually keep around one of the components, a 68 solar mass main sequence star, and I merge actually not two, but three of the components into a single 230 solar mass star. It turns out that during these resonance encounters is a really great way, these 3 and 4 body encounters is a really great time to start these runaways mergers, because it turns out that during these sort of chaotic mini close passages, I have a lot of close passages between my star and stellar components. And if I merge two objects, it's actually really easy to just pluck off another one from the binary. So even during this first encounter, we produce a 230 solar mass star. And so what I'm going to do is I'm going to show what this looks like over the next few mega years. This goes on and on and on and on. Just keeps accreting and accreting more stars in the cluster as the radius gets larger and larger. And actually, this is only showing major mergers, so to speak. We actually are not showing things where the companion was below 5 solar masses. This overall chain had about 1,000 mergers in it. And that's over the first less than 8 million year timescale cluster, right? So in doing this, we end up with a core helium burning star. It keeps accreting more and more main sequence and core helium burning stars, even sucking up entire binaries in the encounter, until at the end, I am left with an 1,100 solar mass core helium burning star that collapses to a 1,100 solar mass black hole. Basically a progenitor seed of an intermediate mass black hole. And you can actually show very clearly, and Kuldeep did this in his paper, that if I parameterize these clusters in terms of this mass density here, right, as I dial down this gamma parameter, this power law parameter, once I get to power gamma's values of 3 or even 2, I really start to get these collisional runaways in essentially every cluster that I look at, right? Just for people that are familiar with this literature, you could think of the profile here as basically a generalization of Plummer. If I set gamma equals 4, I get the Plummer sphere back. So that's cool. We can actually form these seed black holes in star clusters. So what does that mean for us observationally, right? Can we form the Omega Centauri intermediate mass black hole? Can we explain the observations? What does this mean for TDEs from globular clusters? So this takes a little bit more care beyond our traditional Hanal method, because it turns out when I put a central point source in the center, it requires a lot of additional sort of care to actually integrate forward. And so you need to be able to handle specifically microphysics dealing with tidal disruptions in both the full and empty loss cone regime. You need to be able to handle gravitational wave mergers. You need to be able to handle binary disruptions. And you need to be able to do all of that on an orbital timescale. But it turns out we plugged all this into the code, spent about a year doing this, and we perfectly recover both the classic cusp behavior predicted 50 years ago by Bacall and Wolf, and even predict the TDE rate in almost perfect agreement with in-body simulations. So our TDE rate is shown in black here. In-body simulations from Baumgart are shown in purple. The blue lines are actually a previous iteration of a Monte Carlo code where they didn't include some of the physics that we did. And by basically handling the loss cone correctly, we actually get a TDE rate basically consistent with in-body in a fraction of the time. Okay, so we have a black hole seed. What do we do with that? So we decided to go back and start with models that basically look like Omega Centauri. These have basically 10 to the 7 particles at birth, something well beyond the scope of direct in-body. And we just plop in a couple of seed masses, one 500 solar masses and one 5,000 solar masses, and we see what this looks like. And it turns out over about 12 gigayears, just pretending that we started off with a single burst of star formation, it's very, very easy to grow a black hole to 20, 30, even 40, 50,000 solar masses. This is entirely powered, not by TDEs, which is what you would expect for massive, supermassive black holes, but it's entirely powered actually by the mergers of stellar mass black holes and supermassive black holes in the cluster. So in this case, what I'm showing here on the left is what is actually powering this black hole growth in both of these clusters. TDEs maybe give you 100 solar masses over 12 million years. But in spirals with stellar mass black holes, you're creating 10,000 or a few 10,000s of solar masses. So what does this mean for upcoming surveys of TDEs? Well, we can calculate what the TDE rate from this is as a function of time. This is showing the rate in terms of number per year per globular cluster. And so it varies essentially from about 10 to the minus 7 to 10 to the minus 8. For those of you that know the TDE literature, I'm just staring at Kishali. No, it's actually pretty low compared to the Milky Way, right? Most predictions for the TDE rate in the Milky Way are around 10 to the minus 4 to 10 to the minus 5, right? So at best, maybe we're accounting for 0.1% of the observed TDE rate. But if I actually ask the question, well, this is just from one globular cluster. We know the Milky Way has 200 globular clusters. We know other galaxies like Andromeda and M87 have clusters even more massive than Omega Centauri, some of which we think have intermediate mass black holes in it. If I had a massive black hole in every one of these clusters that looks like Omega Centauri, what would I actually get to in terms of the rate? And it actually looks like anywhere from 1 to 10% of the current TDE rate could be explained by TDEs in old globular clusters like Omega Centauri. This is very cool for two reasons. One, these are lower mass stars than you typically talk about in terms of TDEs, right? These aren't like big helium stars or big O stars. These are like mostly low mass evolved stars. And two, these are predominantly going to be off nuclear TDEs, right? Things that we see that are clearly offset from the centers of their galaxies. And so this is something that we're really, really hoping we're going to be able to improve on with Rubin LSST and eventually the Argus array at UNC. At that point, we're hoping when we start seeing thousands of TDEs per year, we can really start to hone in on how many of these things are happening in the centers of galaxies versus the outer regions of galaxies. We can also talk about what is actually driving the black hole growth in terms of IMRIs. And it turns out here, right, most of the black hole growth is actually powered by the heaviest black holes in the star cluster. So I get a nice peak at 30 and 40 solar masses. These are all sucked up by the central massive black hole first. And then as I basically push all of these into the massive black hole, I start processing through the less and less massive black holes in the cluster. The IMRI rate here is wild. It's actually comparable to the same predictions from the Milky Way. IMRI stands for extreme mass ratio in spiral. It's a very exciting potential gravitational wave source for LISA, because it both helps you probe the centers of star clusters, the centers of galaxies, and the strong field relativistic regime. And so what happens is over time, this IMRI rate decreases, but the rate that we get overall in the local universe, ballpark around 10 to the minus 7, is pretty similar to the estimates for the Milky Way. And this is only per globular cluster. And so if there were multiple globular clusters per galaxy like this, the IMRI rate might actually be dominated by low mass globular clusters like this. Just as a quick aside for the LIGO people in the audience, I know I said I wouldn't talk about LIGO, but there's one quick thing that's interesting. If I have all of my black holes going into the central massive black hole like this, completely kills the LIGO rate, kills it dead. This is from a paper in prep by Tom Wu, who's a graduate student in my group. I'm showing basically a massive cluster model with 10 to the 7 stars, and I'm showing the number of black holes that you get, the number of mergers you get as a function of central massive black hole mass. When it's 0%, when I have no central massive black hole, this model produces 1,300 binary black hole mergers. This is sort of the classic big clusters that we talk about when we're talking about dynamical formation of binary black holes. The second I put a massive black hole in there, the rate goes from about 1300 to 10. And basically keeps at that level regardless of black hole mass. And so essentially, if every globular cluster had a massive black hole in there like this, it would completely kill the LIGO rate dead. All right. So that was the massive black hole stuff I wanted to talk about. I'll spend the last maybe 10, 15 minutes or so talking about streams. And so to that end, I'm going to rush through a little bit of the cosmology side of this. But I'm going to go back to this plot that I showed earlier where I said these are the two ingredients I need as a modeler. I need a good in-body model, which we have, and I need some good initial conditions for my star clusters. Now, the latter is a little bit difficult, right? We've never seen globular clusters formation. They very famously formed it in the high redshift universe. And so what about cosmological simulations, right? Can we go look very closely at, say, the fire simulations or some other zoom-in simulations and start to get good initial conditions for our star clusters? And so this is a project that we've been working on for about 5 years or so now in different iterations. It's called the Great Balls of Fire project, or Fireballs. I cannot take, name was entirely Mike Grudich. So it is 100% on him. But the basic idea was the following. And this project, by the way, is a colloquium in of itself. So I'm just going to go through this with a couple of movies and 2 slides. So we start off with M12I, one of the fire simulation galaxies that looks basically like the Milky Way, or more or less like the Milky Way at the present day. From this simulation, we find all the giant molecular clouds that look like they're collapsing inwards and going to form stars. And then we use a series of cloud collapse simulations from Mike to map the properties of those star clusters, of those collapsing giant molecular clouds, onto initial conditions for star clusters. Then, using CMC, we integrate those star clusters forward to the present day, giving us a z equals 0 population of star clusters that was, at least as well as you can get in this field, inspired by the initial formation and evolution of the galaxies they lived in. So we've already got about 6 papers out of this. The first couple by Mike and then myself looked at the cluster formation and evolution. There were a series of papers that looked at the massive clusters and the massive black holes. These are massive LIGO black holes in these. But the one I want to talk about right now is actually the last one of these that came out just this month. It was led by Non Panathan Paisel, who is a Carnegie Fellow, looking at the stellar streams that are formed by these clusters as they're pulled apart by the M12I galaxy. And so just to give you a sense of what this project looked like when it was done, here's a good HST observation of the M12I galaxy. This is edge on and face on, right? And here are the star clusters that survive to the present day. The sizes correspond to mass. The colors correspond to young clusters for the red clusters. The blue ones are globular clusters. And the green ones here are actually globular clusters that were formed ex situ, so by dwarf galaxies that were then later on accreted by the main galaxy. Because this is a zoom in of a zoom in, I can really sort of flex this difference in scales here. Each one of these dots is actually an in-body simulation evolved from the formation of the cluster to the present day. And so these are star-by-star zoom-in simulations with basically as small spatial resolution as we need embedded within the kiloparsec scale M12I galaxy. Right? And so when we did this, right, what this gave us was a suite of star-by-star simulations with initial conditions that are at least moderately believable, or the best we can do at any rate, that we can then couple to our in-body code and really follow the evolution of these things forward in time, right? The galaxy, by the way, if you're curious, formed about 148 globular clusters that survive to the present day. Milky Way has about 160, maybe 10 or 20 more hiding behind the bulge. That's pretty good in terms of numbers. There were some things that didn't agree well. The ages and the metallicities were a little bit off. And actually our star clusters were more core collapsed than what we see in the Milky Way. But other things like the masses, the radii, and the galactocentric positions, we actually got mostly in good agreement with the Milky Way globular cluster population. The nice thing about doing this is that in addition to inheriting the initial conditions, the star clusters also inherit the weird mass loss behavior inspired by their host galaxy. So what I'm showing is what these 3 clusters here, what their masses look like over time. And what's really weird about this, if I look at it, is that the masses just have these discontinuous jumps, right? They sort of fall at very random intervals. And what's happening here is that we extracted from the simulation the galactic tidal field experienced by each one of these clusters over time, and we fed that into the in-body simulation in order to self-consistently strip stars during close, paragalacticon passages, disk passages, anything that should be stealing stars away from the cluster more rapidly than just two-body relaxation, we incorporate into the models. So we did this for about 900 clusters, about 150 survived to the present day. And so what can we end up doing with this? What do these streams actually look like? So this is the paper that Nand just put out and published this month. And so for our first paper on this, we basically looked at two clusters from this in a very, very strong zoom in to really understand what the stellar streams from these clusters actually look like. So of our two globular clusters, we just called them in the paper GC1 and GC2. GC1 is on a moderately eccentric orbit, an eccentricity of about 0.4. GC2 is on a very eccentric orbit, so eccentricity of 0.7. And one thing you notice just looking at the right-hand side here, so this is showing the number of stars ejected and the mass of these clusters over time, and on the top you're showing where they are in the galaxy over time, is that almost all of the mass loss occurs at paragalacticon, right? So all the mass loss occurs basically right next to the center of the galaxy when my tidal field is strongest. And so what we ended up doing was integrating these forward. So the procedure actually here was the following. Let me be a little more careful on this. We took our star cluster simulations. We kept track of every star that was ejected from that star cluster simulation and the properties it was ejected with. The mass, the age, the velocities, all the fun things you care about for stellar stream production. And then we went back into a basis function representation of the galactic potential and re-injected those stars self-consistently when they were ejected from the cluster into this representation of the galaxy. And so what you see over time are both GC1 and GC2 orbiting around their galaxy and losing stars over time. What you also notice, if you spend a lot of time staring at streams, these do not look like the clean, very thin stellar streams you see from particle spray and other codes, right? They have a lot of weird behaviors. They've got weird little over densities in some places. They have weird little fanning behavior. If I slow this down, right, it's really obvious that these have some features that actually look pretty similar early on to like cold thin streams, and then some stuff that just looks really weird. Like here I've got a thin cold stream, just a massive over density here. And so the first stream, GC1, has a long thin stream that is consistent more or less with globular cluster streams in the Milky Way. But if I spread this out and look at it the way that streams people normally do, I actually end up seeing some pretty weird behavior, right? I see my progenitor is right here, right? I see a long thin stream, and I also see this weird over density about 40 degrees behind the progenitor on a great arc, which is pretty bizarre. This is not something that is actually the result of an encounter with a subhalo. That's what you might naively initially think. This actually comes from what we think is long-term interactions with the disk over many, many orbital cycles. And so the big part of this project was trying to understand what do we actually want to pay attention to, and what do we want to be careful with when we're looking at stellar streams and trying to understand properties of the galaxy from that. And so another thing that we looked at is the alignment between the stream track or between the stream and the track itself. One interesting thing about this is that how aligned the stream is at any given time. So how aligned the most recently ejected particles actually are with the rest of the stream depends on where you are in the orbit itself. Now, this is dangerous because the alignment between the stream and the orbit is often used as a way to constrain the shape of the halo. And what we're showing is that this is actually dependent on the phase itself. Here's a third thing that's a little bit unique to this compared to particle spray. Oftentimes you imagine the progenitor actually lives in the middle of the thin stream, right? But that's actually not the case. We show this in the second globular cluster in GC2. In this case, the progenitor is in the outer parts of the orbit. It's in this big sort of blob at the end here, but the thin stream is predominantly still at the closest point of approach to the galaxy. It's predominantly still at paragalacticon. In this case, this comes from the stream's eccentric orbit. Now, the orbit in this case is eccentric, but it's not atypical for streams we observe in the galaxy. So this is just a few of the key things to watch out for when doing particle spray that we've learned so far. The next iteration of this is actually going to be doing this for every single stream in the galaxy. So this is the 30 that we've got so far. You can already see how it starts mixing in here and starts producing an entire galaxy's worth of streams. Eventually, what we want to do, the eventual goal of this is to produce an entire synthetic Milky Way of streams as a way to make predictions for Roman and Rubin, right? And to start actually tuning detection algorithms. So I have 3 minutes left. I do not want to talk about a new in-body code because 3 minutes is not fast enough to do that. What? Okay, in that case, I'll just put my conclusions back up. Thank you so much.
Right, we'll take questions. And for those on Zoom, feel free to leave questions on the Zoom chat.
Great talk. Going back a little bit to the comparison between n-body and the Monte Carlo method, I think you convinced us that the average properties of the calculation seems very solid, and even some prediction for some event rate. But I was wondering, we're interested here sometimes in, for example, in the context of high energy events or gravitational waves, in things that are pretty exotic pathways of evolution. We have the same problem in stellar physics, obviously. And so I was wondering if, have you tried comparing the statistical properties of the extreme events in your n-body and Monte Carlo to see that they have the same properties? I think that would be very important to understand if you really can simulate the same type of events.
So the last time we've done this, this was from, God help me, my PhD 10 years ago. When we were looking at that, we focused pretty monomaniacally on the bulk evolutionary properties and then the production of binary black holes, because this was also early 2016. And in those cases, the distributions are basically spot on. So the production of binary black holes agrees essentially perfectly with n-body. And that kind of makes sense, actually, from almost an Eddington type argument, right? The entire thing is regulated by the amount of energy you need to hold the cluster up against continued collapse, which means my binary hardening rate has to be set by the energy requirements required to hold up the whole cluster. So as long as I'm getting basically the evolution of the half mass radius and the ones around it correct, I have to be getting the binary black hole hardening rate. Now that unfortunately only applies to the most massive things in the cluster. If I'm interested in, for instance, millisecond pulsars and other things like that, then I do need to check those species individually. The last time we did that, we found good agreement between, I think it was stellar collisions and a couple of other things. Basically, we haven't checked every single exotic population, though.
The one you focused on, you checked.
Yeah. And typically for me personally, like the Monte Carlo method works shockingly well. I don't fundamentally trust it if we put some brand new physics in there, especially something that changes the overall evolution, unless we have an in-body run we can compare it to.
Thanks.
Yeah, thank you for the nice talk. Is it too overly simplistic to think of the conditions necessary to have this runaway IMDH mass growth as just I need some sufficiently large effective cross-section that is either governed by the stellar mass runaway that you mentioned until you reach a black hole massive enough such that in its compactness it's still large enough to serve that effective cross-section? Or is that a wrong way to think about it?
I mean, no, I think that's a perfectly valid way to think about it. Like fundamentally what's determining this, right, is just the n sigma v collision rate, right? Like I have some number density, I have some velocity dispersion, and I have some size of my target. At some level, if I have a high enough density, everything else sort of washes out. There's some density where I will always get a stellar runaway, right? That just kind of has to happen on some level. I think the interesting uncertainties here are actually what happens if I change my stellar evolution, or I do my post-merger radii calculations much better than we currently do with population synthesis, right? If I get much smaller stars, does that decrease the collision rate? I mean, the answer has to be yes. The other thing that we do totally ignore in this, and every in-body person ignores in this, with the exception of the handful of people doing cluster and hydro simulations, is the gas, right? If I go back and look at this very fun merger tree from Kuldeep, you'll notice that this all happens in less than 8 megayears, right? If I go by the old school picture that the gas expulsion in a cluster is predominantly driven by supernova, that hasn't even started by 8 gigayears. And so this entire process is occurring in the time frame when I still should have a large amount of residual gas. Now, that's just using supernova feedback. These massive stars should also have, hilariously strong winds, which could in of itself be enough wind-driven feedback to blow out the rest of the gas. But neither I nor I think anyone else can adequately tell you what the winds should look like for a 1,000 solar mass star.
Thanks, that was great. Could you go back to the mass loss evolution of GC1 and GC2?
Yes, that was right here.
Yeah. Okay, so the fact that the mass loss, the amount of mass that's actually lost at every pericenter or whatever, perigalacticon for Megan, is that it's not consistent with just shot noise. It's like much bigger, the variance in terms of how many stars are being lost. What is causing that variance? Like why in one shot do you get 5,000 stars complete, and in another shot you get just 100 or something?
You mean during each one of these peaks specifically?
Yeah, which are presumably the pericenters, right?
I mean, they're the pericenters, but they're not necessarily at the same radius, right? So, right, this is
a huge amount of variation, right?
There's not a huge amount of variation. This one, all right, let me see which one drives this one. This one is, yeah, this one is actually not the smallest one. I would have to go back and look at that specific one. The thing is, there is a bunch of additional stuff going on in the galaxy at this point, right? There's, the disk, there's the bulge, there's a few small subhalos which are actually resolved in the BFE at the resolution that they cranked this up to. I don't, however, know what drives that one to be larger than the other ones. This is, I mean, on the one, this is how I feel in general about these large daisy chain simulations. On the one hand, you can do some really cool stuff with them and get some really, really, very interesting, very diverse results out of them. The downside is it makes it a little bit difficult to go back and see, here's the one thing that caused this one feature, which is both a blessing and a curse in some ways.
Yeah, I guess I'm curious of whether it's internal dynamics or tidal field.
It's almost certainly the external tidal field in this case. So the thing about CMC though that is bad, and this is why I'm a little sad I didn't get to talk about the new in-body code, is that CMC cannot handle a non-spherical tidal potential.
I see.
So we can calculate the tidal radius, we can strip stuff off. And I mean, this makes sense, right? Because like I harped on how CMC is a spherical code. How do you put a spherical cluster into a non-spherical external potential? And I mean, the cheap way to do this and the way we do it, it's actually not even that cheap, is I just calculate the Lagrange point. I have some additional corrections for the time it actually takes something to escape to the Lagrange point. And then I just strip anything that passes beyond that. So you should read this in the CMC case as the Lagrange point is just moving in and out in response to the changing tidal field. To do this properly, what you would have to do is actually go back and replace and basically do an explicit orbit integration in a changing potential while still doing Hanel's method, which is what I didn't get a chance to talk about, but is what our new code does and should allow us to resolve this. Downside is it's a lot slower. Still much faster than in-body, but slower than CMC.
Can take one question online. Brian, do you want to unmute and ask your question?
Hi, Carl. It's Brian. Thanks for the nice talk.
Hey, Brian.
Could you say something about these the rate? Well, there's sort of two sub questions. Something about the rate of stellar emeries versus black hole emeries onto the central IMBH, and then for the stellar emeries, what do you assume about how they interact when they meet the black hole? Do you assume they just merge, or that they undergo stable mass transfer onto the IMBH?
When you say stellar emeries, you mean gravitational wave driven stars falling into the black hole?
Yeah, I'm guessing those are, So are those irrelevant or, yeah?
For the masses we looked at, they essentially are irrelevant. There's nothing we found that undergoes that that isn't TDE'd first.
Okay. So the black holes are able to circularize through gravitational waves and come in on circular orbits, but the stars can't, unlike in galactic nuclei. Okay.
Yeah.
Okay. All right. Thank you.
Right. I think we should continue over the reception. Let's thank Carl again.